This lecture is on electron configurations, and an electron configuration is the way in which the electrons are arranged around the nuclei of atoms. So what is the pattern of these electrons around this nucleus? That is an electron configuration. The quantum numbers are the basis for electron configuration, and there are four: N, L, M sub L, and M sub S. N is the principal energy level, or the principal shell. L is the angular momentum. That's going to include the subshell and the shape. M sub L is the orientation, so it's going to be referring to which orbital axis it's on. And M sub S is the spin of the electron. We are only going to focus on N. We are only going to focus on N, which is the principal energy level. So the first four principal energy levels. So when your principal quantum number is 1, the sublevel that is present is S. There's going to be one orbital in the S sublevel. When you get to principal quantum number 2, you have S sublevel and you have P sublevel. S again has 1, but P is going to have 3 orbitals related to it. When you get to the third principal energy level, you're still going to have S, you're still going to have P, but now we're going to introduce the D sublevel. S is still 1 orbital, P is still 3, and D has 5 orbitals. When you get to the fourth quantum number, you still have S, you still have P, you still have D, and now we're going to introduce F. S is still 1 orbital, P is still 3 orbitals, D is 5, and F is 7. So you're going to see as we move across the periodic table, we're going to add principal quantum numbers. After the fourth, it's going to remain S, P, D, and F with 1, 3, 5, and 7 orbitals respectively. Again, the S sublevel is 1 orbital, and that shape is a sphere. So 1 orbital can hold a maximum of 2 electrons. We said the P sublevel has 3 orbitals. It is a dumbbell shaped. If there are 3 orbitals, and each orbital can hold a max of 2 electrons, 3 times 2 is 6. D, we said, has 5 orbitals. This is a clover shape. Again, each orbital holds a maximum of 2 electrons. 5 times 2 is 10. And then F is 7 orbitals. It's a very complicated shape, so it doesn't actually have a name. And since each orbital can hold 2 electrons, 7 times 2 is 14. So this is the S in the spherical shape. This is the P. So there's 1, 2, 3 orbitals, and each orbital can hold 2 electrons. So you have the probability of finding 2 electrons here, probability of finding 2 electrons here, and the probability of finding 2 electrons here. Here's D with its clover shape, and we said there were 1, 2, 3, 4, 5 orbitals. So these orbitals overlap to give us that D sublevel. And then here's F with its very complicated shape. And so F has 1, 2, 3, 4, 5, 6, 7 orbitals. And again, each orbital can hold 2 electrons. So somewhere in this crazy shape of space, you could find 2 electrons. So there are 3 rules defining electron configuration. The first one is the Aufbau principle. And the Aufbau principle says that electrons are going to enter orbitals of lowest energy first. Orbitals within a sublevel are always going to be of equal energy. So your 3p orbitals are all going to have the same energy. Within a principal energy level, S is always the lowest. So if you get to the third principal energy level, we said we have S, P, and D. S is going to be the lowest principal energy level there. Exceptions to this Aufbau rule are the chromium and the copper groups. If you follow the Aufbau principle, you're going to get this. Chromium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now I understand this looks like a jumble of letters and numbers, but I will explain how we get to this. So if you're counting across, this chromium is in the 4th D slot of the 3rd sublevel, and copper would be in the 9th D slot of the 3rd sublevel. These two are not happy like this. They are completely unstable. So they're going to shift one electron out of here and into this last d orbital. So they're going to take one electron from here. So 2 minus 1 is 1. So this is going to become 4s1. This one electron is going to flip into here. So 4 plus 1 is 5. So that's going to give you 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember, we took one electron out of here and shifted it into here. 3d5. So this is that extra electron that came from here. They're much more stable, half and completely filled, than partially filled. They do this on their own. It's not like someone's manipulating them. They automatically flip that electron over to be more stable. The Pauli exclusion principle says that an orbital may hold at most 2 electrons. And in order to occupy the same orbital, those 2 electrons have to have opposite spin. Spin is a quantum property, and it can either be clockwise or counterclockwise. And we're going to note the difference with an arrow pointing up and an arrow pointing down. Hund's rule says that when electrons occupy orbitals of equal energy, one electron is going to enter each orbital until all of the orbitals contain one electron with parallel spins. And I know that's a lot, but think of it as you're eating at a family dinner. Everybody needs to get their food at least once before somebody comes back through and gets seconds. So you need to make sure everybody has an arrow on their orbital before you come back and assign that second orbital, a second electron, sorry. All right, so if we look at this periodic table, it's broken up into blocks. The first 2 columns, this is your group 1A and your group 2A, are going to make your S block, and helium over here. Your P block is group 13 or 3A through 18 or 8A, starting at neon. Your D block is going to be your inner transition, so it's going to start at group 3 and go to 12. So all of these are D. And then your F are your inner transition down here on the bottom. And we will go through and label this in class and do some practice problems.